So remember from before, we talked about the effect of A on a function. So the A is for a vertical stretch, compression, or reflection. So if your A value is greater than 1, you have a vertical stretch. If you have a value that is between 0 and 1, you have a vertical compression. And if your A value is less than 0, you would have a reflection. So we're going to add a new variable to consider, or new letter to consider. And this one is going to control our horizontal expansions and compressions. So this is the number that is in front of x. In general, if k is greater than 1, the function is compressed horizontally by a factor of 1 over k. So for example, if your k value is 2, then the x-coordinate is multiplied by 1 over 2. If k is in between 0 and 1, so a fraction, the function is stretched horizontally by a factor of 1 over k. So if k is 1/2, then the x-coordinate is multiplied by 2. When k is less than 0, just like our A value, the graph is also reflected in the y-axis. So you should note that the x-coordinate of each point in the base function is multiplied by 1 over k, or the reciprocal, to figure out the new transformed point. So let's take a look at a couple examples. In our first example, we have a graph that is compressed horizontally by 1 over 2. So what that means is we're going to take every x-coordinate in our base function and multiply by 1 over 2. So in our original function, we'll make a little table of values here. We've got x and f at x. 3 x values that I can identify are my first one here at -3, -2. My second one at 0, 5. And then my third one at 4 and 0. Now, in order to get my transformed function, I'm going to take my x values and I'm going to multiply them by 1/2. My y values I'm going to leave alone. So that means my first x value, instead of -3, is now -3 over 2. And I'm going to actually do these in red so I can graph them a little bit better. So -3 over 2. My second x value is 0. And my third x value is 2. I've only done a transformation to my x values of my graph, so my y values stay exactly the same. So my new graph, I'm going to plot in red. So I've got -3 over 2 and -2. And then I've got 0, 5, and then 2, 0. So you can see that my graph, my x values, are twice as close together, or I've compressed it by a factor of 1/2. I have one invariant point, which is right here, only because my x-coordinate was 0, so multiplying that by 1/2 didn't do anything. My domain, let's do my domain. I'm going to stick to the same color. My domain is now smaller. It's going to go from my smallest x value, which is now 3 over 2, to my largest x value, which is +2. My range is still the same. So I go from my lowest y value, which is -2, to my highest y value, which is 5. So the next example that I'm going to look at, I'll do in purple, is this one right here. So my graph here has been, not compressed this time, stretched horizontally by a factor of 2. It has also been reflected in the y-axis, which is a horizontal reflection. So I'm going to start with my original table of values. I've got my x, f at x, same as I had before. And I've got -2, 5, and 0. I am going to take my x values and I'm going to multiply all my x values by -2. So instead of -3, I would get +6. Instead of 0, I would still have 0. And instead of 4, I would have -8. I haven't done any vertical transformations, so my y values are going to stay the same. Then I'm going to plot those points. So now I've got 6, -2, 0, 5, which is again another invariant point. And then my last point is -8 and 0. So I've got a function that is wider than my original. It's been stretched and it's been reflected as well. My domain now is quite a bit larger. I'm going to go from my smallest x value to my largest. And my range still happens to be the same because I haven't done any vertical transformations. Let's look at another example. Example 2 uses the absolute value function. So the one that we're going to look at is the function y equals 4x. This one is our transformed function. And so the first thing we need to do is identify our parent function. So our parent function is y equals the absolute value of x, and we're going to sketch that. So I know that that one sort of looks like a V. Put on a couple points here. I'm going to make those two lines as straight as I can. And then I have my function here. So y equals the absolute value of x. That is my parent function. The next thing I need to know is what the transformations are to that parent function. So I see that I've got that 4 in front of the x. That means that it is horizontally compressed by a factor of 1 over 4. So 1 over k, where my k value is 4. So now I'm going to graph those transformations. So in order to do that, I'm going to start with a table of values for my original function. And I'm just going to choose values that happen to be divisible by 4. So I've got -4 and 4. I've got 0 and 0. And then I've got 4 and +4. So that means when I transform, I am multiplying all my x values by 1 over 4. So my new x values, I'll do these in red, are going to be -1 and 4, 0, 0, which is an invariant point, and then I've got 1 and 4. Here is my invariant point. It doesn't change under the transformation. And then I can plot those on the graph. So I've got -1 and 4, and I've got 1 and +4, 0, 0. So my graph is much skinnier. It's been compressed horizontally. The points are 4 times as close together. So then my domain and range of the transformed function. So my domain is all of my x values, so that is the same. Still -infinity to infinity. My range also happens to be the same, 0 to +infinity. If I were to graph a reflection of the function in the x-axis, okay, reflecting in the x-axis, this is actually a vertical transformation. So my new equation would look like this. And that would be like I put a mirror on my x-axis and I flipped my points down. So then I would have -4 on both sides. Whoops. -4, 4, 0, 0, which is invariant. And now my function looks like an upside down V. If I wanted to graph a reflection of the function in the y-axis, this is a horizontal transformation. My equation would look like this. Because the function is symmetric, it actually doesn't change. So I'm just going to draw my purple on top of my original red graph. And this would be y equals 4x. It would also be y equals -4x. My blue graph represents my vertical transformation, that reflection, y equals -4x. Next example is where we're given a point. And in this one, we're looking at the coordinates of the image of this point on each graph. So where would the point be if you transformed? So in my first one, I've got y equals f at 2x. This is a horizontal compression by a factor of 1/2. So I know that I'm going to take my x value and I'm going to multiply it by 1/2 or divide by 2. So my new point, my original point is 4, 3. My new point, I'm going to take my x value, multiply by 1/2, and keep my y value the same. This point here, or this transformation expression, has two different transformations. So the first one is the 3. This is a vertical stretch by a factor of 3. And then I also have a horizontal stretch by a factor of 2. So my points are being spread out. My x coordinates are being spread out. So that means I'm going to take my original point, vertical stretch by a factor of 3. That affects my y coordinate. So I'm going to take a 3 and I'm going to multiply that by 3. My x coordinates are also getting stretched out. So I'm going to take that and I'm going to multiply by 2. So my new point is 8, 9. The last example that we're going to do is we're going to figure out the k value for each transformation. So the function y equals f at x has been transformed to y equals f at kx, and we're going to determine the value of k for each transformation. So if I have a horizontal stretch by a factor of 5, that means that my k value has to be less than 1, greater than 0. So my k value would be 1/5. If I have a reflection in the x-axis, my k value just has to be less than 0, so -1. And the last one, if I have a horizontal compression by a factor of 0.5, which is the same as 1/2, and a reflection, that means that I'd need a k value of 2 because I'm compressing by 1/, that k value, and I also need my k to be negative. That is a summary of different examples of applying horizontal reflections, stretches, and compressions.